Okay, so I re-uploaded the notes for the governing equations. There was a very small mistake, and it was the same mistake that's on homework 2, problem 5. So please re-upload those when you can. And I also uploaded some new notes on the governing, not on the governing equations, but on interfacial boundary conditions. And we will definitely be starting those today. Um, so last time we had ended up deriving conservation of energy, or not really deriving it, but very briefly going through it, because it's the same total energy equation that you guys may have seen in your gas dynamics classes, or fluids 1 or fluids 2, or something like that, or even convective heat transfer. You guys have seen this before. And for a reacting flow single phase, this equation here is no different than the master governing equation of total energy that you guys derived back then. And the reason that it's no different is because all of the chemical energy, as was stated in the previous lecture, is in the enthalpy of formation term. Now, it's a classic homework problem, but if you remove the enthalpy of formation from your definition of the energy, then you have an additional heating source term minus Q dot, where Q dot equals the sum of omega dot I HF I naught. Okay, and so that's really bad. I need to move that somewhere else. And this Q dot is equal to the sum of omega dot I HF I naught. And that's if you remove the sensible, or if you remove the enthalpy of formation from the definition of the total of the sense of, or of the internal energy. Okay, and so for a reactive flow, if you see a heating term due to chemical reaction, that means that their internal energy does not have the enthalpy of formation included. If you see this term missing, that means that the enthalpy of formation is included in the definition of the energy. And some folks like, and there is an equal number of folks who like doing it either way. In our own codes, we include the enthalpy of formation just because we are lazy, and that's how, if you look up NASA data and things like that for the internal energy, the enthalpy of formation is included just by their definition. So it is less work for us to include the enthalpy of formation. Okay, so I'm not going to go through it, but then we have this heat flux vector, and the heat flux vector, recall, is this heat conduction term plus an interdiffusion term plus a second order Dufour effect, which is normally neglected. And this interdiffusion term is just the sum of rho yi times the diffusion velocity for species I times the enthalpy for species I. Okay, and then if the flow is smooth, you can use the equivalent of the product rule on these two terms here, and collect them like we did with conservation of mass, or with conservation of mass, momentum, and species mass. And when you do that, and if you cancel out conservation of mass, you wind up with this form here. And again, you can only do this operation if the quantity rho v times Et is differentiable. And if you have a discontinuity in your flow, such as a shock wave, then across the shock, this term here is non-differentiable. Okay, and so you cannot do this step here. Okay, and so this would be the total energy equation in non-conservative form. Okay, and so now with the energy equation, that's an equation that you see written in about a bazillion different forms. If you work with compressible flows, like my group does, or Dr. Stewart's group does, or Bala's group does, we tend to work with it in this form right here. Just because that's called conservative, and that's basically the form, and it's called conservative because that's the form that comes from the most generic RTT. It's the form that naturally comes from the system, and if you solve this and use proper numerics, you are ensured that if you have a insulated box of material, if you are simulating a reactive flow inside a well-insulated box that does not allow heat or mass to leave through it, if you use conservative form, you will be guaranteed that the total amount of energy in your vessel, no matter what's happening inside of it, will be perfectly conserved. Whereas if you use the so-called non-conservative form, that is not the case. And there are various modeling and numerical reasons for that. And again, if this was a course in numerical combustion, I would discuss those in more detail. But if your flow is smooth and you don't have shock waves and things like that, then there is essentially no difference between these two equations here. Okay. Now, as I said before, there are various forms of the energy equation. Sometimes you'll see them in a temperature form, sometimes you'll see them in an enthalpy form, and they are all valid. They're all the same equation. So I'm gonna show how you put this into a temperature form. But first, we are going to transfer to an enthalpy form. And before I do that, I need to remove the mechanical energy from this total energy equation here, because remember, this total energy is defined to include the kinetic energy. And so I'm going to remove that from this equation right here. Okay, and so how you derive, you guys have probably seen this in your Fluids 1 class, so I'm just going to go through it very quickly. But there is a mechanical energy equation that you can derive, and you derive it by just simply taking the velocity vector and dot it with the entire momentum equation. Okay, and so that's actually a very straightforward operation. The only trick that you need to recall is that basically v dot times v dotted with the substantial derivative of the velocity vector is equal to the substantial derivative of 1/2 v dot v. Is that basically you can move this inside. And if you were to use the product rule on this, you can convince yourself that that basically this statement is true. And after you guys get experience with this stuff, this is an identity that that you see actually quite a lot being used. So eventually, after you get experience, you just sort of learn to recognize it. Okay. But the crazy ones with the cross products and stuff, I myself do not remember those, because every flow that we deal with is massively compressible, and so I can't even do any of these steps here. Anyways, so we're going to take v dotted with the entire momentum equation, which we derive the momentum equation over here. And so I'm just going to take it and then dot it with the velocity vector. And so, and I'm going to use this identity for basically v dot dv. And then there's no other super fancy tricks that I can do for any of the terms. So I just simply have v dot grad p, v dot the divergence of the stress tensor, and v dot with say the body forces. So if I do that, I wind up with this equation here, which is the mechanical energy equation. And so, and then you can do the same operation for momentum equation in total energy form. They are equivalent. Again, with the exception of the smoothness assumption that is buried into this equation here. So now we have this equation. It's really for the kinetic energy. And this is the energy that I want to remove from the total energy equation. So basically what I do then is I subtract this mechanical energy from the total energy equation. Okay. And to do that, I will note that since since the total energy is the internal energy plus the kinetic energy, I can say that dEt dt is equal to dE dt plus d1/2 v dot v dt. Okay, and so that's just using whatever the property is where you have two terms added together. That name escapes me at the moment. So I'm going to use this identity here on dE dt, and I'm going to take the entire total energy equation, and I'm going to subtract from it this mechanical energy equation here. Okay, and so I'm going to do that operation, and so I'm just going to subtract them, and so you can see these two terms cancel out, and then I have a bunch of leftover terms here where I have the divergence of P times V minus V dot grad P. Well, you can look at the identities that I showed at the very top of this document, and this just turns out to be P times the divergence of the velocity vector. I have this term here. I have the divergence of the velocity dotted with the viscous stress tensor, or actually the stress tensor, minus V dotted with the divergence of the stress tensor. And it turns out that that is the stress tensor double dotted with the gradient of the velocity vector. This term here is actually viscous dissipation. And you can prove, which may have been done in some of your other classes, I'm not going to do it here, that this term is greater than or equal to 0 at all times. And so this term here, it's actually a heating term to the sensible energy equation. It's basically converting mechanical energy into thermal energy irreversibly. Okay, and we have done nothing, and the body force term goes away, and we have done nothing with the heat. We've done nothing with the heat flux. Okay, and so basically using that, we have derived the energy equation. It's no longer the total energy. It does not include kinetic energy anymore. And sometimes they'll just write the energy equation. They will not tell you exactly what form they are looking at. But if they are working with this form, look for the P times the divergence of the velocity vector. That will clue you in as to that basically this is the internal energy, not the total energy. Okay, so this would be an energy equation that is another form of the energy equation. Again, perfectly valid in smooth flows. Now, if we want to convert this to an enthalpy form, we can note that E is equal to the enthalpy minus P over rho. And then I just take the total derivative of E, and which means I take the total derivative of H minus P over rho. And you can show that this is dH dt minus the product rule on this term here. So this is dP dt times minus 1 over rho times P times d1 over rho dt, and that d1 over rho dt is just d rho dt over minus rho squared, and I have a plus sign here because I have a minus and a minus here, so you have d1 over rho dt equals minus 1 over rho squared d rho dt. And again, you can work through the definition of the material derivative to basically convince yourself that basically this step here is true. And so now note, from conservation of mass, we had that d rho dt equals minus rho times the divergence of the velocity vector. So I can take this equation here, and in particular this d rho dt, and substitute in minus rho times the divergence of the velocity vector right there. And if I do that step, I get this equation here, where this is minus p over rho times the divergence of the velocity vector. Okay, so now my goal here is to convert this to an enthalpy form. And then, so I'm going to take, so this here is just dE dt. So I'm going to take this definition of dE dt and sub it into the internal energy equation right here. And so in doing that, I get this term right here, and none of the other terms have changed. Okay. And you can show that basically this term here that you can show through some simplification that this equation here just turns into what's called the enthalpy equation right here. Okay, and so it's just rho dH dt minus the material derivative of dP dt, because the 1 over rho is here, because the rho times 1 over rho here cancels, minus the divergence of the heat flux vector, plus the viscous dissipation. Okay, and so this here is the enthalpy equation. So that is another perfectly valid form of the energy equation. So far we've seen 4 of these, and then you can show that's actually problem 5 on your homework set, that you can show that you can take this enthalpy equation here and derive a temperature equation by assuming that H is a function of T, P, and species composition. You can basically substitute that in, use some Maxwell's relations and things like that, and you wind up with that rho times Cp dt dt is equal to this huge mess over here. And you have this beta T here, and beta is the thermal expansion coefficient, which is defined like this. Okay, and so, so basically you guys will be deriving this, you guys will be starting from here and deriving this for your homework. Because there are so many forms of the energy equation, it's sort of, it becomes useful practice to learn how to manipulate them. Okay, and this thermal expansion coefficient right here, that comes naturally from the pressure term here of the enthalpy. Okay, and this grad HI term here, that's the term that I was missing in the homework write-up. I messed up a vector operation, and that just comes from, you guys will find out where that comes from. Okay, but notice that when you cast this into temperature form, the equation explodes into a huge number of terms. You have a material derivative here, you have heat conduction Dufour, viscous dissipation, you have this material derivative of pressure multiplied by the thermal expansion coefficient, you have a chemical heating due to chemical reaction. Again, you're no longer conserving energy, and so there does have to be some sort of heating term to the energy equation, plus this leftover enthalpy or diffusion heat flux term because they don't exactly cancel out. Okay. And for an ideal gas, the thermal expansion coefficient is just 1 over T. And the enthalpy for species I is a function of temperature and temperature only. So then you can show that grad HI is just dHI dt times grad T, which is just the specific heat of grad T. And so if you make these substitutions in many combustion books, you will find the form of the temperature equation that is listed in the books. Whereas the equations that are listed in many of the books are generalized, or they're not generalized. They are specific to a mixture of ideal gases. Here, because of this term right here, and the fact that I left this term alone, this is valid for even real gases. Okay, but when you work with real gases, I'm not aware of anybody who solves the temperature equation. They tend to solve the total energy equation. Okay, and then also there is a second form of the temperature equation where it's based on CV, and the starting point for that temperature equation is not the enthalpy equation right here. It is the internal energy equation right here. And you'd go through a process similar to what you guys do for your homework to drive that. But this is the more common form that you see. Okay. So are there any questions with this? Okay. So we've derived mass, momentum, species mass, and energy. There's a whole lot of equations, and really to get familiar with them, you gotta just get experience, and so that's part of what the homework is for. And there are a lot of them, so I will summarize them right here. In conservative form, these are valid for basically any flow, but they are especially used for compressible high Mach number flows with shock waves and things like this. And so here you have conservation of mass, conservation of species mass, which has the diffusion velocity. And I apologize for not drawing the arrow all the time. I get lazy, and also my handwriting isn't the best. I'm well aware of that. And so doing all these little flourishes to distinguish all the different V's gets sort of messy for me sometimes. And we have this, that shouldn't be double prime. That should be just omega dot I. We have this chemical reaction term here to account for the change of species mass due to chemical reactions. And you have, if you have NSP number of species, you have NSP species mass equations. We have the Navier-Stokes equations right here. And I guess I shouldn't say Navier-Stokes. It becomes Navier-Stokes after you use Newton's law of viscosity here, because this equation here is also valid for even solid mechanics. You just have a completely different stress law. And then we have conservation of total energy right here. Okay, and so if you solve these and handle these terms right here, you can now simulate reactive flows or basically model them. Okay, and so that's just a summary of the governing equations. And then now same thing in non-conservative form. These would be used in more traditional combustion if you want to model a standard combustor. In a standard combustor, you normally don't have shock waves unless your combustor is having a really bad day. And so typically, they will often solve many of the equations using the smooth flow assumption, and they will solve them in this form right here. Okay. And then I just have the temperature equation here written with the CP form. Now note, every now and again when I review a paper, that and you'll find that when you work through problem 5, you'll find that the specific heat naturally goes outside of the derivative. It does not go inside of this derivative right here. No. So this form, even though CP is outside of the time derivative, this expression here is valid for cases where the specific heat is non-constant. In fact, you can only move in specific heat inside of this derivative if it is constant. That is the only time that you can do that operation. Okay, and so even though rho and Cp are outside of the derivative, this expression here for the temperature equation is valid for a flow where both rho and Cp can change. Okay. So are there any questions with these? Again, I'm just summarizing the governing equations. And so now we got all these equations written down. Now you can see how all the pieces that we've been going over for the past 2 or 3 weeks, where we got the chemical reactions, the diffusion velocity, the viscous stress tensor, and the heat flux vector, how it basically all comes together. And so if you want to model a generic reactive flow, you need to consider all of these effects. And now that's not to say that all these effects are important for every combustion application. As was brought up, there are some applications where we don't need to consider the heat flux vector or the viscous stress, such as a detonation, such as a detonation, which we'll get into later on. Okay.
Professor, I know you've explained this a couple times, but can you just quickly go over again the assumption we make to go from the conservative form to the non-conservative form for smooth flows? Like I know you showed us for continuity how we couldn't break out the derivative. Could you just show that again one more time?
Yeah, so for continuity, we have partial rho, partial t, plus the divergence of rho v, right? And so we want to get this into a quote non-conservative form. And the procedure is the same for all of the equations. And so to do that, we need to use the product rule on this term here. So if you use the product rule, you have the divergence of a scalar with a vector. And that identity is A, this is equal to A dot times the gradient of phi plus plus phi times the divergence of the vector. Okay, but you can only do this operation right here. You can only do this if the term in here is differentiable. That is the scalar is differentiable, this vector is differentiable, and their product is also differentiable. If there is a discontinuity in the flow, like a shock wave, like that, this quantity phi a at this discontinuity, we can call this phi a. This quantity, the divergence of phi a, is not differentiable at this discontinuity, and so this identity here, which assumes that phi a is differentiable, is no longer valid. So when you work with continuity, you'd have partial rho, partial t, plus v dot grad phi or grad rho plus rho times the divergence of the velocity vector. And this here is by definition d rho dt. And so basically for every equation, whether it is yi, for say species mass, you have a y here, you got to do this exact same step every single time. And so if the stuff inside of the divergence is not differentiable, like you have a discontinuity, a true discontinuity, then you cannot do this step. If you cannot do this step, then you cannot rearrange the equation into this form here, which means you cannot rearrange it into a form where there's a material derivative. Okay?
And when we have a shock, are all properties considered to be non-smooth across the shock, or are some considered to be differentiable function across the shock?
Like mass fraction will be smooth across a shock wave. It depends. Like I said, for those of you who've had gas dynamics, the Riemann, um, the shock, yeah, in for the terms that we have here, all variables except for mass fractions will be changed by the shock. Mass fractions, for those of you who've had gas dynamics, mass fractions are called Riemann invariants, and Riemann invariants, and that type of Riemann invariant is not changed by the shock. Which basically makes sense, is that the shock itself is not changing the identity of the fluid. Is that the molecules themselves are being are not being converted due to the shock. Even in a detonation, where there's a shock causing the chemical reaction, the shock and the reaction are you guys will learn, are two different steps. And so the mass fraction itself is the only variable that for this type of flow, or for these type of single phase equations where that is valid. But the quantity, the divergence, even though mass fraction itself is physically okay, but the quantity rho yiv is not okay. Okay? And so even for species mass, where the mass fraction itself is okay to differentiate across the shock, because it's not going to be changed by the shock, is okay, but the quantity rho yiv is not. Okay?
Okay, yeah, that was helpful. Thank you.
Okay, and so, yeah, you just need to look out for that. And that's why you never, when you solve, if you have a detonation or something like that has a massive shock wave, or if you're modeling a scramjet or solid fuel ramjet, they tend to solve the equations in this form right here. Okay, if you're dealing with a traditional combustor or a car engine or a gas turbine, they will often solve them, often but not always, solve them in this form here. Even in those flows, some folks are starting to solve the governing equations in this form right here. Just because these forms here deal with acoustic waves and things like that a bit better than the non-conservative forms.
So for here, the conservative form and the non-conservative form for continuity equation are equal. Is that just?
Yep.
Okay.
Yep. Yeah, they're the same equation, and they are normally solved in this form. Yeah, if you take fluids 1 or fluids 2, like I said, once you get to the non-conservative forms, there are probably literally hundreds, at least a dozen different ways of writing the equations. I just wrote one. Some folks, there are low Mach number approximations that you can make where you do work with continuity in this form, but you use for incompressible flows, you would basically use this as your continuity equation. And so if your code base that you are using is based off of incompressible flow, you need to modify this, and so you add a source term, and that's equal to minus 1 over rho d rho dt. And so there's all sorts of games that you play for if you work with non-conservative equations. Okay, and so in a way, if you look at a modeling study of folks modeling gas turbine combustors or car engines or something like that, you need to pay attention to the equations that they are actually solving. And basically different groups will solve different forms of the conservation equations and make various assumptions. Okay. Now, now we have the governing equations. Now there's all sorts of terms that we need to model. And so for both types of models, you need an equation of state of some sort. And for low Mach number flows, you can actually use what's called the Incompressible Ideal Gas Law. And that assumes that P is equal to a constant. And then you would say that P naught equals rho RT, or rho equals P naught over RT. Okay, this would be called an incompressible, a so-called incompressible ideal gas. Because in combustion, you can be changing the temperature quite a lot, and so you do need to account for that expansion and that change of density. But in a lot of combustion applications, the pressure is constant, and then they'll do other tricks where they'll say P is equal to this P naught plus a P prime of X and T, where basically this pressure here is the term that goes in the Navier-Stokes equations, because you need only the pressure gradient, and this term here is used, and then the sum of these two, and basically this term here is this P naught is the term that is used to evaluate the density. Basically, you are separating the sort of fluctuating fluid mechanical pressure from the thermodynamic pressure. But for a compressible flow, you cannot do this. So this would be for low Mach number only. Okay, and so there are all kinds of games and stuff that people who work in low Mach number combustion that they deal with. So if you're using a commercial package or open foam, I would really suggest that you look into the manual and see what form of the equations that they are actually solving. I think Fluent does something like this, or at least it did 15 years ago. Okay, but in general, so I'm talking here, oops, you can't see my hands, but here I'm talking for a generic flow where it may or may not be fully compressible. And so you need, in either case, an equation of state model, whether it be this incompressible ideal gas law or a formalized equation of state. And so we have spent quite a bit of time going over those. You need a transport model. So that is, you need to pick a different an appropriate model for your thermal conductivities, your binary diffusion coefficients, the viscosity, and if needed, the thermal diffusion coefficients. I didn't go over those, but if you guys need them, you can definitely look them up. Then you need a diffusion, if you're using mixture average diffusion, you need a diffusion potential model. So remember that the diffusion potential for an ideal gas was just the gradient of the mole fraction times xi minus yi times grad p over p. Or if you have a real gas, you need to use this form here, which you guys will be getting experience with in the homework. And this barrow diffusion term here is often neglected, but not always. And I list these here as a choice, even though physically this is, if you have a real gas, this is the more correct form to use. As you guys will find out in problem 3 or 4, I can't remember which one, this term absolutely explodes into a big giant mess. And so what happens is most folks who model this will basically wind up using the ideal gas form of the diffusion potential, which that can cause problems. And when we go over some supercritical combustion later on, I will show basically one example of where basically that can go wrong. Okay, and so a lot of folks will basically, even though they're using a real gas, they will use this form of the diffusion potential half the time intentionally, and I suspect the other half of the time not really knowing that there's a more physically correct version for real gases. Okay, and so even if you never use this form here, it's still important to be aware of it. Okay, so now we picked a diffusion potential. Now we need to pick a diffusion velocity model, which may or may not use the diffusion potential. If you have fixed law, then you don't need to worry about the diffusion potential. You just basically use this form here. If you use mixture averaged, sometimes called Curtis Hirschfeld. Same difference. Okay, is that basically we have this mixture average mess here to determine the diffusion velocities, or you have the Stefan Maxwell, where the Hirschfeld-Curtis uses the diffusion potential directly. Stefan Maxwell, right here, which this is technically for an ideal gas. I have yet to find a paper that actually lists a version of this that's valid for real gases. I'm going to keep looking for one and maybe write that equation down later on. But yeah, and so you have all these different choices. Then you need to pick a heat flux model. That's a bit more straightforward because there's only one of them for all the different types of flows. But you just need to choose whether you include the Dufour effect or not. And normally that is neglected. Okay, so we have all the transport. You need to pick a chemical reaction model. For those, there are many. Even for methane, there's not one master methane reaction mechanism. There are a whole bunch of them that are calibrated for different applications. So if you're modeling a reactive flow and you look through the lit to look for a reaction mechanism, usually the folks who give out the chemical reaction mechanisms are very explicit about where they are applicable and where they are not applicable. Make sure that you, if you have a choice, if you can, use a chemical reaction model or mechanism that is valid for the flow regime that you will be modeling, because you can't use a you cannot use a methane air reaction model that was calibrated for stoichiometric combustion at 1 atmosphere, and you cannot use it to model detonations you cannot use them to model fuel-rich detonations where the equivalence ratio can be, say, 2, and the pressure can be on the order of 100 atmospheres. And so basically those are not in the same regime, and so you need to pay very close attention to that. But also note that sometimes you may only have one chemical reaction mechanism to use for some fuels. And there you may, in such cases, you have no choice but to use a suboptimal chemical reaction mechanism. So, but just be aware of that. Okay. So you've chosen your transport model, you've chosen a reaction model. Then the last choice you need to make is what version of conservation of mass and species mass to use. And so one option is to solve all of the species mass equations. Then when you need the density, you just basically sum up all the species densities. And so all the species mass equation, you're going to get the quantity rho times yi. If you want the total density, you just basically sum all these up. And you do not explicitly solve conservation of mass. Option door number 2 is to solve all but one species mass equation and explicitly solve conservation of mass. And so there you know the density directly, and you can figure out and so you would know the density directly because you are solving these, and you'd know the mass fraction directly. And so but you solve this for basically all but the very last species. And to get the mass fraction for the very last species, you just use that the mass fraction is defined such that they all sum to 1. And so the mass fraction for the very last species is just 1 minus the sum of all the other mass fractions. And the caveat with this is you need to choose that last species very carefully. For folks who do this, it's often the diluent, like say nitrogen in the air, which has a high mass fraction that is often not changing. You run into severe numerical issues if you were to pick this this last species to be an intermediate where the highest mass fraction is, say, 10 to the minus 5, and it comes and goes in the course of the reaction event. And so if you choose that as your last species, that tends to cause a lot of severe numerical problems. And if you do not have a species that is in excess everywhere, like nitrogen and air, then it's often better to opt to do this version of it here. Okay, and so these are all things, I know this is a little bit overwhelming right now, but these are all things that as you work with these equations and you work in combustion, you will eventually get get used to these. Okay, so are there any questions on that? Okay, so we will get started real quick. So we know the governing equations. So now we need to discuss what are called interfacial boundary conditions. Because then after we know that, we know how to handle we know how to handle the equations, and we need to know what happens, since it's of course in multi-phase combustion, we need to know what happens at material interfaces. So when combustion, we often are concerned with gas-liquid interface or gas-solid interfaces. So for example, we have a burning aluminum particle here. We have solid fuel here, or if it's molten liquid fuel, that can there can be some vaporization of aluminum at the surface of the particle, and that aluminum is going to diffuse away, or that aluminum vapor is going to diffuse away from the surface. It's going to mix with the air, which is diffusing towards the surface, and they're going to meet to form a flame, and we'll be discussing this in more detail later on. But in order to model this, we need to know what's going on at the surface so that we can have an appropriate boundary condition to apply, so that we can model the gas phase combustion, but yet account for all the vaporization and all the other effects on the aluminum particle. And you have a similar issue if you are modeling a solid propellant combustion, which will be one of your guys' computer projects, where basically you have this receding solid surface that is basically burning backwards, and there are products coming off of it that are basically burning. And so you would need to know how to handle this interface here so that you get the species mass and energy and then energy correctly. Okay, and so to apply these boundary conditions, we apply the RTT or the Reynolds transport theorem to derive either boundary conditions on one side or the other of the surface, or jump conditions across a surface. Okay, and it'll become more clear later on what I mean by those. And so to derive that, let's just consider before we call it, we'll just basically go over what the idea here is we consider a generic control volume at the surface. Okay, and so we have, say, a material interface here. This could be a liquid here, and this could be gas over here. And so I'm going to label one of these surfaces, or basically one of these materials, as being on the plus side, and another material as being on the minus side. So you could consider this minus material being liquid, and this plus material being gas. And so now we want to figure out what happens, basically what does conservation of mass say across the surface? How do you handle a species mass balance across this interface? And so here we need to define all sorts of quantities here. So basically I will say that the surface here is moving, can move at general with some velocity VI, because you could imagine if this was a droplet, the droplet could be deforming, it can be jiggling around, and it can be flying around in space. And so in general, the surface here can move, and you need to account for that. And I'm going to define x as, I'm going to attach the coordinate system to the surface of the to the interface. Now, when I choose this control volume here, I'm going to choose a clever control volume. I guess it's not clever on my part, it's clever on the folks who came up with it, is that I'm going to choose a very skinny control volume here, and that the height of it into either into the plus side or the minus side is a very small epsilon. And then the idea here is I'm going to use the normal Reynolds transport theorem or control volume analysis with the assumption that that this epsilon is going to tend towards 0. It's not going to go to exactly 0, but basically we are choosing the top side of this control volume to barely be inside of the gas. Okay, and so basically I am zoomed in, by a factor of 10 million here. Is that basically the very top of this control volume here is just barely above the surface, and basically the bottom of the control of the control volume is just barely below the surface. Okay, and so and when you do that, you no longer need to worry about the sides because they're so small that there's basically no flow that can go through them. And so we will discuss those points in more detail on Friday's lecture.